Hello, everyone. You are listening to Uncomfortable Truths with Euclid Phoenix, where I talk about politics, religion, and other BS that I find interesting. Today, I will talk about wormholes. Few ideas in physics capture the imagination like wormholes. They promise shortcuts through space, instant and stellar travel, possibly even time travel. They show up everywhere, from serious theoretical papers to movies and science fiction epics. But here's the real question. Are wormholes physically possible? Or are they just strange mathematical artifacts in Einstein's equations? Let's dig into what we actually know. What is a wormhole? In 1915, Einstein introduced general relativity, a theory describing gravity as the curvature of space-time. Space-time can bend, it can stretch, it can twist. In 1935, Einstein and physicist Nathan Rosen found a solution to the equations describing a bridge connecting two distant points in space-time. This became known as the Einstein-Rosen bridge. Today we call it a wormhole. Mathematically, it's like holding a sheet of paper. Two distant points on the surface, fold the sheet, punch a hole through the both layers, instant shortcut. In theory, a wormhole connects two faraway regions of space, or even different times. The problem, they collapse instantly. Here's where things get serious. The origin Einstein-Rosen bridge isn't stable. If you tried to pass through it, that would pinch off, collapsing faster than light could cross it. Sealed shut instantly. In other words, it's not a tunnel. It's more like a fleeting ripple. So physicists asked, could a wormhole be stabilized? The exotic matter requirement. In 1988, physicist Kip Thorne and colleagues explored what it would take to keep a wormhole open. Their answer, you'd need exotic matter, not just unusual matter, matter with negative energy density. This kind of matter would repel gravity instead of attract it, push space-time outward, and prevent collapse. We have observed tiny quantum effects like the Casimir effect that create negative energy densities in extremely small amounts, but enough to hold open a microscopic wormhole. That's a different scale entirely. We have no evidence that such matter exists in usable quantities. Are wormholes just mathematical tricks? Here's the honest answer. Wormholes are mathematically valid solutions to Einstein's equations, but not every mathematical solution corresponds to physical reality. Physics history is full of equations that allow exotic possibilities that nature never uses. The key question is, does the universe allow stable wormholes to form naturally? So far, we have no observational evidence, nor confirmed natural mechanism, and no experimental hint of macroscopic wormholes. That doesn't mean that it is impossible. It only means that it is unproven. Wormholes, black holes. Some early speculation suggested black holes might be wormhole entrances. The issue is that real black holes contain singularities, and anything crossing the event horizon is crushed. There's no evidence of a safe passage through. Modern research suggests that real astrophysical black holes likely do not function as transversal wormholes. However, quantum gravity theories are still exploring this frontier. The quantum twist. ER equals EPR. In recent years, some physicists have proposed a fascinating idea known as ER equals EPIR. R suggests that quantum entanglement, EPR, and Einstein-Rosen bridges, ER, may be deeply connected. In simplified terms, entangled particles might be linked by microscopic wormholes. These wouldn't allow travel, but they hint that space-time geometry and quantum physics may be intertwined in unexpected ways. This is speculative but serious theoretical work. Could we ever build one? To engineer a traversal wormhole, you'd need enormous energy, like stellar scale, exotic negative energy matter, control over space-time curvature, and a theory of quantum gravity beyond current physics. That's not just advancing engineering, that's civilization type it on the Cadavid scale engineering. We're nowhere close. The time travel problem. Even if wormholes were possible, they introduce paradoxes. If one mouth of a wormhole moves at relativistic speed, time dilation could cause the two ends to become time shifted. Travel through it, you might arrive in the past. That creates classic causality paradoxes, the grandfather paradox, and the closed time curves. The grandfather paradox is a logical contradiction in time travel theory where a traveler goes back in time and kills their grandfather before their parent is conceived, preventing their own birth. Many physicists suspect the universe prevents these solutions via unknown consistency constraints. Stephen Hawking proposed the chronology protection conjure, essentially that physics forbids time machines. We don't know yet if that's true. So what's the verdict? Wormholes are mathematically allowed, consistent with relativity, explored in serious theoretical physics, but they are also not observed, not experimentally supported, not known to be stable, dependent on exotic matter we've never seen. Right now they live in the space between hard science and eloquent speculation. Why this matters. Even if wormholes turn out to be impossible, studying them pushes physics foremost. They force us to confront the limits of relativity, the nature of space-time, the relationship between gravity and quantum mechanics. In other words, wormholes aren't just sci-fi tropes. They're pressure tests for our understanding of reality, and until we have a full theory of quantum gravity, we can't say definitely whether they're impossible shortcuts or doors we simply haven't learned about how to open. Thank you for listening. You can check out my website in the notes below. Have a good day.